Hey guys, what's up? RU1R0 here. So in this video, we're going to cover heap exploitation on Linux, which was a topic, which was an area that I was not thinking that I'm so good at. I'm doing mostly reversing and exploitation on Windows. Of course, I know and I have some experience on exploitation on Linux as well for Stack Overflow vulnerabilities, for different techniques, bypass some mitigation techniques as well. But heap exploitation on Linux and the different techniques comes around that was a topic that I was afraid to touch for a long time. I knew some stuff, I knew some techniques, but it was so distributed in my head and I was not so great at it. And finally, I found this really cool Udemy course by Max Kemper. He's a genius. Definitely go check it out. What I'm going to talk about in this video is mostly focusing on his content on Linux Heap Exploitation 1 course. There are 3 courses that he gives on Udemy. And that was exactly what I need because he covers everything perfectly and all these empty spots in my head that I was not so sure about. Everything is filled now. This is so good. I almost finished all of his 3 courses, but I definitely go suggest you to check it out. We will just cover one technique, one Linux heap exploitation technique in this video, the House of Force, but there are so many different techniques and of course, it becomes more advanced when the techniques gets harder. But in this way, in this video, we will get into some tools, some command line tools to use and reverse the binary. We will try to understand the mitigation techniques with a tool called checksec. We will try to understand the whole journey on heap exploitation of a Linux binary. And yeah, we will learn few stuff in this video. Like I said, I wanted to give a disclaimer before you guys jump into the video. I did not create any of these binaries, and the content is very parallel to what you would see in Max Kemper's Udemy course. Kudos to him. It was an incredible course, and he's the expert. So if you want to learn more about heap exploitation, go check it out. This is just me, as always, getting in my corner and repeating some stuff that I learned myself. And yeah, hope you will enjoy this video. As always, please drop a comment at the end of the video and press the like button. And if you're ready, let's jump in.
All right, let's dive right into our content then. So first, let's start talking about glibc. What is glibc? And from there, we will move on to the heap explanation, and then I will start giving a bit of introduction on how to set up your environment, which kind of tools to install, and then we will start to learn our first technique on heap exploitation. So for glibc, glibc is an open source library that takes the form of a shared object, which is the Linux equivalent of a DLL file. glibc is a fundamental part of many Linux operating systems, and without the glibc library, you would not even be able to shut down the operating system itself. So let's see, how do we see that? Let's find an operating system glibc shared object with the LDD command. Let's see, for binls, for instance. I'm using LDD command, which stands for list dynamic dependencies, and it will list the shared objects that a binary relies upon, as you can see in here. So we want to see about the glibc. So if I grab only grep for libc.so, as you can see the version in here, and you can list the shared object, the glibc, in this way. So we're talking about how important this glibc library is, and let's see how much of a disk usage does it have. So yes, as you can see, as the disk usage of this glibc library is 2 megabytes. So it's not a giant file, but the operating system is depending on this. If you remove this file, none of these applications, not even Firefox or any of these applications will work. You won't be able to shut down the operating system. So this is very vital for the operating system itself and also the application that depends on this binary. So as it is important, there are different exploitation techniques that we will cover in these videos. This video will just cover the House of Force technique, which is the easiest technique that we will see in the first place. And in this way, we will get ourselves familiarized with the tools that we're going to use in the rest of the videos as well. And this will be basically the intro to our first heap exploitation. So we talked about glibc, so how important it is. What is heap? So the code that glibc provides is a dynamic memory allocator, which is known as malloc. I'll write it like this. So let me repeat again. The code that glibc provides is a dynamic memory allocator, malloc. These dynamic memory allocators are used when a program cannot know the size or number of objects it needs prior to runtime. And malloc allocates chunks of dynamic memory to the processes at runtime. And the chunks come from heap, and they are basically simple large blocks of memory that malloc requests from the kernel. So let's see the syntax for malloc. What does it look like? Say, let's use the function malloc, and let's write number 16 here. So when we see the syntax, 16 stands for the size of the memory that we will allocate, and A is the pointer to the memory. These are only things that you need to know right now about the malloc function and how we will use it in the future. So keep it in mind how to use the syntax and what does this mean. 16 is the size of memory we will allocate, and A is the pointer to that memory. Cool, so let me show you the tools that we're using. I'm right now using Ubuntu, let's see here in Safari, Ubuntu 18.04.6, which is by Beaver. Of course, there are more up-to-date versions, but this will be more compatible with our exploits that we will use. So there are a few tools that we need to install as well. One of them is pound tools that we will use a lot during reversing the binaries to exploit these heap exploitation. The other one's pound debugger, pound dbg, and one gadget. Go ahead and install these on GitHub repository. They are publicly available. Install it. This is super easy to install. It has its installation one line of instructions, let's say. It's super easy. I will not dive into this. So I'm assuming that you already installed it. If you want to go ahead and do the same step-by-step guide on your site. Cool. Let's go back to our virtual machine and let's start learning about the tools, and also let's start reversing the binary already. Cool. Let me delete these comments and let me go to my directory. Like I mentioned, this is from the Udemy course. However, I checked before I create the video in case there's like problem of sharing these binaries in case they're not publicly available, but there are many GitHub repositories that shares the same binary, so I'm assuming they're publicly available. So I'm not copying any content or anything. I'm just like, I just went through these courses that I got from Udemy and they're super cool. And they really filled my lack of knowledge on heap exploitation in many areas that I'm really happy about. Like the picture's full in my head now. So yeah, go ahead and get these binaries online on GitHub. And we will start with House of Force, the first technique. Let's go to that directory. Oops, or start two of these, of course. And we will start with the demo binary to understand how to use the tools and to understand what kind of binaries that we're gonna work on. So let me clear this and let's load this binary in GDB. Demo, I don't have this close terminal. Let's get that. So we load the binary with GDB. As you can see, we're using the pound dbg tool. It automatically loads itself as we installed it. So we will have more understanding on memory with different comments that comes with pound dbg. It's a very cool one. I definitely suggest you to use it. So let's put a breakpoint at main function. With B, you can also write break, but these are like the shortcuts for PyDBG, and I will say run. If you want to understand, of course, this is given a bit of understanding on registers, the disassembly code, and the source code in here, which we are going to start looking into at the moment. This is basically a very small C program that uses malloc functions so that we can understand how this works and how we can exploit a vulnerability on heap like that. So this also shows a bit of understanding on stack backtrace. There's nothing that you need to worry about at the moment. I want to see more of a source code at the moment, so I will write the following comment to just deal with the source code section. I will say set context sections code. So let's say context. And as you can see, we're just seeing the source code now, so we don't need to deal with the other stack or register information. So what does this code do? In the main function, we defined in the same syntax as malloc. This is A, which is the pointer to the memory. 9 is the size of the memory allocation. We're using malloc function, right? And then we are requesting more memory from kernel. As you can see, there are different sizes in here, and we will just see how this looks like when we request a memory. So you can use the comment via map, which will print a memory map basically for this process, but you will not see an entry for the heap yet because malloc request did not start at the moment. And we did not request any memory from kernel yet. And this is how it works. Malloc will not request any memory from kernel until it needs it. So right now you are not seeing anything for heap, which is supposed to be the blue color, right? So let's go with the next comment for the next line of code to be executed, which is going to be this one. So I'm just going to say next, or I can just say n. Any of these should work. So as you can see, the cursor went to the next line. And let's see with heap is chunk. You're seeing the top of the chunk in here that refers to here. These information will be on top of your heads very soon. I'm just like trying to explain what is what. You can also check the pointer A, which is supposed to be defined here. If you do that, it also shows the memory. It also shows the address of this pointer, as you can see in here. Very cool. So what is this 21 that we are seeing in here then? It's called size field, and it means the total sum of bytes that make up the chunk. So you will always see it in here in the beginning of this chunk that's been created in here with the malloc function that's been allocated, and in here on top of it you will see the size field all the time. So what is the size field? Why is it 21? So we are using 24 bytes of, let me write it in here, I will delete it later. So we're using 24 bytes of user data in here like that. And we are also using 8 bytes of size field. Sorry, my German keyboard. So this is 8 bytes of size field, 8, 16, 24, 24 bytes of user data. So it's total of 32 bytes or equivalent in this 0x20, right? But we see 0x21 because malloc's chunk size increases in increments of 16 bytes. And that's why you are seeing x21. All right, so we got more familiar with the binary a bit, a few comments that we will use more frequently in here. We check this out. So how do you close GDB with quit command or Control D on your keyboard, as you prefer? So let's give an introduction to our vulnerable binary. So we will be loading it with the command checksec. So let's see what this comment output gives us. It's a 64-bit binary. It's compiled with full railrow, which is a mitigation technique. It's PIE, position independent executable. If not, we'll know its address on runtime, so it says no PIE. That's good to know. It's full railrow reg gets set, and NX is enable. However, this will not affect us, as in this example, we will not be exploiting glibc itself, but rather we will be exploiting an individual binary. So if we would be exploiting glibc, we would be caring about full railrow or NX enabled, as that would affect us. Good to know and good to understand the output of this comment. So we will run the binary in GDB now, and we will see the functionalities of the program. Let's say GDB and house of force binary is running. So without putting a breakpoint, I will just say run to see what kind of functionalities do we have. So the program displays two address right now with puts and heap. So the address of puts function within glibc and also the heap address here. So these are good to know. The program is printing these for us. So the option 1 here, as you can see right now, there is 0 allocation out of 4 possibility. The option 1 will allow us to request up to 4 chunks of heap memory while using the malloc function. Let's see the option 1. It asks for size of the heap. It's basically ask for the amount of memory that we want. Let's explore the first option. Let's say 24 for the size, and I will just put some dummy data here. And it just continues asking for other option. And as you can see, malloc just looks as 1 out of 4, meaning we already used one-time memory allocation. So what you can do here with GDB is that you can press on Control-C to break in GDB so that you can have this PAM-DBG beautiful screen to start reversing to binary. So let's check with this, as we already allocated one memory, use malloc function once. So we will see this one. So let's see what's happening in here. So the heap start address is in here, 603000. As ASLR is disabled for this one, it will always start in the same address, so you will always see this address as the beginning. So malloc is allocated 0x20 size chunk with 24 bytes of user data as we defined in the size field with the first option that I typed probably 30 seconds ago. And as you can see in here, 24 bytes in here. This is the size field, as we explained before. 21, this is actually 0x20, which is 32 bytes data, which means these are all 8 bytes, 8 bytes size field and 24 bytes of user data, right? So we understand this now, and the user data that we sent is written in here. This is the niv line corresponding for niv line, and you can see the user data that we sent, 4 bytes of y in here. So the niv line that's been mentioned in here. Cool. So let's continue exploring the binaries, other options. So I will just say continue. And as you can see, if you press again, we are getting the other options. So what I can do, let's say the second option, which is a target. As you can see, we have this target data in here, and we want to overwrite the target data. And since this binary is non-position independent, we'll know the address of the target on runtime. What's going to happen now? Let's break in GDB again, Control-C. We go back there, and we will dump code word for target. See what do we see in here. Let's also check with xinfo target comment, get more information. So we're seeing x, which is represented with 58 in here, 0x58. So if you want to see where it resides, as you can see, it resides in data section. If you look at the memory address in here, so now we verified that this target resides in the data section of this binary, and we get more information like that. So how we can have an arbitrary write on this target address. So let's go back, say run again, and we're in the beginning again in the function. And I'm just gonna go with the first option and the size. And for the size field, I will write a lot of junk data here. I'm writing Y. When I do that, and let's break in GDB to see what's going on in here right now. We obviously overflow something. Let's check with this. So what's going on in here? We overflow the chunk and overwrite the size entry, as you can see in here. So we have 8 bytes of overflow while writing into these chunks, and top chunk overwrite is the focus for the House of Force technique. So the technique is called House of Force, and we are overwriting top chunk. So we are focusing on top chunk overwrite, which is in here. So if you want to learn about the libc version as well, you can use vmmap libc command. For instance, if you have libc 228, it doesn't have top chunk integrity check. So this mitigation was introduced for the later version. That's why we were able to overflow this data. So this is just another very small nuance. Text editor, and I will try to explain some information here so that we can have a strategy. So this is the low address, and then we have application. Sorry, I don't have diagrams here, so I will just try to explain verbally. We have the heap, we have the libraries, and we have the stack. And of course, this is going to the high memory address, right? So what we're trying to achieve in here, if we overwrite the top chunk of the heap, we can overlap the sensitive data in the libraries. We're going like that, and then the stack regions. And remember that our data, our target was residing in data section in the lower address. So if you write a really big data, it will overlap the top chunk of the heap, and then the libraries, and then stack. And since we reach out to the end, it will go back to the low address. So it will go back to the low address and request another large request from malloc, which will be serviced by this heap's top chunk and overlap the binaries data section. So let me repeat the strategy again. If you do not know the memory structure, that's what it looks like from low address, low memory to high memory, the application, heap, libraries, and stack. And we're trying to overwrite the heap's top chunk. And if we write a very large data, what happens is we overwrite libraries, we overwrite stack, and then since it reaches out to the end, it goes back to the low address again, and we continue overwriting until we reach out to the data section, which our target is. So that's our strategy. So let's see how the exploitation looks like. I don't need to send more. I'm closing without saving. So let's close GDB with quit comment. Let's clear this. So if you go to this directory, there's this Palm Tools template, py. This is like a introduction to heap exploitation that you do not know how to write these Python scripts yourself. So this is like a template. We will just change few lines of code. So I'm just copying this file, let's say exploit.py, and I will start exploring exploit.py in here. So let me use nano because my virtual machine is a bit unstable. So I will edit this in nano, but I will start GDB from V later. So we copied this file and so that we can work on our own copy. So we will modify only the example section in here. As you can see, we have some information already. There's some example comments are included, example lines are included in here. Let's go to V. I want to show you how you can start GDB from V inside. So we will just keep this in here. So what I'm going to do is press escape and write the following shortcut. Here we go. So there, these 3 lines of results is the log info calls that we already had as example lines. So if you see hit and return to see one of our 4 chunks is allocated already. But let's exit this one and let's start modifying our file. Okay, I'll modify in nano. So the first line that we will write will be allocating some memory, as we did in the demo file and also in this binary before. We want to allocate some memory with the size 24 we did as before, and then we will try to overflow the data to the top chunk, and then from there we will try to send so much data so that we can reach out to the data section to alter target data. So I'm given the size 24, and I will be writing the data y, and I will be sending this for 24 times. After that, the next 8 bytes will send after y's will overwrite the top chunk, right? So let's append that value as a second argument of malloc, and you can use pack64 or p64 function, which is a wrapper around struct.pack, which comes with pound tools. And we want to override a very large value. So we'll try the biggest 64 value by using F16 times. Cool. As always, we are going to use the same command, escape, and then exclamation point dot slash percentage. You can just run it like that, GDB. And we can also put no ASLR in here to specify no ASLR, to disable ASLR. And we will run this command to see pam debugger and the other terminal. So let's make this small so we can see everything together. So let me see. Make this a bit bigger for us to see better. So we have pam debugger in another screen in here. I will run this command, which we can see in here. We write the ffffff. Next 8 bytes is written already on the top chunk size field. That's very nice. Let's go to the next phase. Let's create pam debugger, and let's go back to our previous screen. Enter comments. We end up with Vim again. I'm going back to nano. Like I said, oh my god, this is ridiculous. To move between the text editors. Cool. The next phase will be we're going to request enough memory from malloc to span the gap between the top chunk and our target data. So we need to calculate the distance between our target and top chunk. So I will write the distance parameter, and I will explain what I'm doing in a second. I'm writing the delta function. So what just happened now? We're trying to calculate the distance between our target, which we are trying to overwrite, and our top chunk, which we just overflowed. So we are using here the delta function, which basically takes 2 parameters, 2 arguments, which is the start address and the end address. start address top chunk and end address is target, right? So the start address is top chunk, which is the leaked address stored in the heap variable. If you remember in the beginning, when we run the application, there were two addresses there and heap was already leaked. So I can just use the variable heap in this way, which will be interpreted in the application without any problem, and start on the heap variable. So we'll add 0x20 in here. Oops, I'll go back here. So 0x20 to that address, to that value, to account for the 0x20 size chunk that we already allocated before in here, so that it can result in the top chunk. So cool, that was the first argument of delta function. So the second one will be the target, right? So in here, the end address will be the target. Those X in the binaries data section that we're trying to overwrite. And I'm writing it with this elfsim target syntax. Sorry, I wrote this wrong, minus. And I'm taking 0x20 away from this value to stop just short of the actual target data so that we do not overflow of 0x20 anymore. So we calculated this distance now, so I need to allocate that with malloc comment again. We will request this and we will write a single byte of garbage into it, which is the character Y. So cool, let's save this. Let's go to Vim again. Escape. Let's write the same. GDB, no ASLR. Oops. Let's run it like this. The new screen is coming here. Control C to break in GDB. And here we are. So let's see what just happened in here. Try to understand if we were successful with the comment that we wrote. I will be writing DQ, dump code word, target minus 16 to see what just happened there. And let's also see the top chunk address in here. We see that the top chunk size field is in here, overwritten with 19, which is set in the program's data section. So you can confirm this with the following comment top chunk. As you can see, the address in here, and the size is also given in here. So that's very good. We are very close to what we are trying to achieve. Okay, we're continuing. Let's allocate another memory. Let's say overwrite. And if we say target, so whenever we go with the second option, as you can see, our target is overwritten. So whenever we ask for more memory allocation, our data will be written every single time. So we will just write this one to our script. Let's kill POM debugger. Let's quit. Say okay. We went back to Vim. Let's quit this and continue in Nano. Like I said, you do not need to do that. My VM is very unstable and Vim is not working properly, so I am lazy enough to fix this. I am instead doing it on Nano, which is a tool that I hate. I'm a Vim girl, but yeah, sometimes we need to deal with this. So let's write the last line with malloc. What we will ask it. We're gonna write 24 bytes of data with data like overwrite. I don't know. It's the first thing that came to my mind. So that should be the same that we were trying to achieve. We're saying save it. Let's go to Vim again. Let's see if our code is there. Yes. Escape. Oops, it's the same format. GDB. Let's do that. Escape and just that. See if it's working in the production condition without GDB. So whenever we check the target, it's written as overwrite. So arbitrary overwrite was successful. We handled it perfectly. So let's see what we've done here again. Let's quit this. So let's go back to Vim and let's try to understand what did we do. So in the strategy, the binary had a heap overflow vulnerability, which allowed us to override the heap's top chunk size field with a very large value. So we convinced malloc that the top chunk was much larger than it actually was, which allowed us to make a very large allocation. And the large chunk was requested, which spanned the gap between the heap and the target data, and we overwrite the target data in this way. So that's great. We learned our first technique. We overwrite heap. So we exploited the heap memory vulnerability. So how are we going to turn this into an RCE? So it is possible. So there's a heap specific way to hijack the execution flow, which is called malloc hooks. Each of malloc's core functions, such as malloc and free functions, has an associated hook, which takes the form of writable function pointer in glibc's data section. So let's go back to our editor and let's start writing a different comment in here. So I will just keep them in a comment so that we would remember what did we write before. So the first line, we're not changing it. It's the basic comment that we write to override the top chunk size field. For this one, I'm putting this in a comment because I need to calculate a different distance in here. Let me write it and then explain it. So how do we calculate the distance? So this time, the distance we want to cover with our very large allocation is the difference between the top chunk and the malloc hook, which we are gonna use to hijack the execution flow, right? We're going to use the malloc hook because it's the only one of malloc's core functions that we can reliably call in this binary. And we don't need the delta function anymore because this time this chunk won't wrap around the VA space like it did before in the previous script that we wrote. So we're writing the name of and we'll subtract 0x20 again from that address like we did before so that the allocation stops just short of the malloc hook, if you remember in here. And we're removing it from the heap address as we already defined in the previous one. So let's execute it as it is. Let me first write this one. This is the curse of the video that Vim is not working properly. All right, so I'm just going to escape and run this in the same format with GDB, no ASLR. Cool, the new screen came up. So let's start inspecting the memory surrounding. I will break in GDB with Control C. Here I am. So I will dump code word, that comment. Let's check for malloc hook. So let's see the top chunk, C20 in here. So the second line that you're seeing in here, the first quad word, will be the malloc hook. So if it's null, like now, it's ignored and calls to the malloc function works as normal. If it's not null, calls to the malloc function are redirected to this address. So we do not want this to be 0. And so we will go back to our script. Let's press in here. Go back to nano so we do not break unnecessarily. So what I'm going to do is, instead of writing overwrite, I will write this with p64, pack64, 0x, say that beef. So let's see if this will work. Let's save this again. And let's go to Vim and let's work as always with GDB and no ASLR option. Oops, we did something wrong. That's good. And let's break in GDB again with Control C. And let's see for the pointer malloc hook. So if this address is not 0 but the dead beef, that means our overwriting was successful, which looks like it's already happening. That's very good. So if we click on, if you continue, and I just clicked on 1, if you go back to our memory, as you can see, RIP is written with dead beef as well. So I think we were successful. We overwrite this malloc hook. Then we call to malloc and we hijack the execution flow in this way. Now let's get a shell as the last step of this exercise. Okay, let's go back to nano again. So instead of writing that beef, I will instead write this. I will execute bin sh. Let's write here libc sim system. So instead of writing this garbage data here, of course, I will be writing bin sh. Do not forget the null terminator here, 0. So let's define the comment in here. So you can check the manual page with men system comments if you want to get more information. So the other Safari comment resides at the start of the second chunk's user data. And of course, don't forget to add this null pointer in here for the bin sh. So it will be heap plus 0x30 and pass that address to malloc with the comment with the parameter cmd as if it was a request size. So let's do that. Let's go to Vim, but this time we're not going to run it with GDB. We're just going to run it as if it would be in production condition. I'm running this. Give me the shell already. If I check for who am I, it gives me root. Cool. So what did we do so far? Let's go back there and let's go to the end of the code. What did we do in here? Let's try to understand again one more time. So as you know, this binary had a heap overflow vulnerability, which allowed us to override the heap's top chunk size field with a very large value. So we convinced malloc that the top chunk was much larger than it actually was, which allowed us to make a very large allocation. And the large chunk was requested, spanned the gap between the heap and the targeted data, and we calculated the distance. And then we gave this garbage data, replacing it with bin sh. We called the system function here. And then we calculated the comment. We write the comment with the heap, and we asked from malloc, as this would be the size field, as this would be the size, which gave us the shell. I know that this may be a shocker. It's a very different technique comparing to the Stack Overflows. But it's very fun. There are so many different techniques that we will see. I will try to create different videos on that. But yeah, since I have my own program, I'm working for my way to OSEE, and I have a busy schedule besides that because I have a day-to-day job as well, which makes me sometimes not create the video in the speed that I want. But there are so many techniques that I refresh my mind about and also learned about from the Udemy course. Let me refer to that again. That's the course that I'm talking about. It's from Max Kemper. That's a very, very brilliant course. I definitely request you to go check it out. My video was basically about the techniques that I knew and also techniques that I learned from these videos, and also aced my skills on different areas of heap exploitation. However, his course is incredible. I'm just repeating his words basically on a way that I'm just showing it in my own VM with how to exploit these techniques. But yeah, he is the teacher, he's the instructor. Just go check his videos. I'm not doing some advertisement in here. I don't even know Max Kemper. Kudos to him for his great training sessions in here. There are also these two courses as well that I bought. It's a pretty intense one because you're learning so many things, especially if you're not familiar with these topics. It will be hard, but I would definitely suggest you to learn it, guys. We learned House of Force in this video. There are different techniques that we will cover, like House of Orange, fast-bin dupe, safe and unsafe unlink, etc. And I will try to cover also the other courses as well. Not other courses, the techniques from other courses as well. But I'm not as good as Max Kemper. He's a pro on this topic, so go check his videos. Otherwise, hope you enjoyed it. As always, drop a comment, and let's see each other until the next heap exploitation video. Cheers, guys.